All right, welcome back. So here we're looking at a second test that will let us check convergence of some series. Um, Again, ratio test is really good when you're, especially if you're dealing with factorials. The ratio test is a really good test with that. Uh, that's one of its better features, just to help when working with factorials. Again, as we saw, it also helps working with exponential functions and some degree polynomials as well. Um, so it has its uses, but it breaks down on some problems. Uh, isn't the greatest thing for some problems. And so we have another test known as the root test, which works really good with powers. Which works really good with powers. And so what the root test tells us is that if we let AK be an infinite series. Again, it doesn't necessarily need to be positive terms or alternating terms. It can be any kind of general series. We look at the limit as k goes to infinity of the kth root of a to the k. So if that's equal to rho, okay, that kind of slanted p there is the Greek letter rho. So rho, if rho falls between 0 and 1, okay, rho falls between 0 and 1. It's greater than or equal to 0, less than 1, then our series will converge. If it's greater than 1, then our series is going to diverge. However, if the limit approaches 1, it turns out the result is actually inconclusive. Actually turns out that the result is inconclusive if we approach 1. Okay? So just like the ratio test, there is a time when it's just not going to work. We're not going to know. Now, why does this work? Well, if rho is equal to the limit as k goes to infinity of the kth root of a to the k, then that means that the kth root of a to the k is approximately equal to rho for a really, really big k. And that would mean that a to the k is equal to rho to the k. Okay, actually, the absolute value of it, which would make this a geometric sequence. If we looked at the series of the a to the k, absolute value of a to the k, that's a geometric sequence roughly for a really, really big k at the end. So being geometric, we know it converges if we're between 0 and 1. And so that's kind of the idea behind why the root test works without filling in all the nitty gritty details. But that's known as the root test. And that's a second way to check convergence. And so what we're going to look at is we're going to do some examples, and we'll see that sometimes the test is really, really good, particularly if we're dealing with series that involve powers involving k. This is when the root test really, really shines. This would have been, I don't even know what this would look like. I don't know if I want to even think about it with the ratio test, how this would look, and if we would even be able to compute the limit of that, the resulting ratio for this. I don't know if I'd even want to think about it. But this will actually be ready made and set up for the root test. Okay, and that's what we're going to be taking a look at. Is we'll actually look at this one here in a little bit in an upcoming video, as well as some other examples where, again, the root test works pretty well. Okay, but the root test, again, the idea is we look at the limit of the kth roots of our sequence. If they're approaching anything between 0 and 1, including, it will converge. If it approaches anything that's bigger than 1, including infinity, of course, then we know it's going to diverge. And if it approaches 1, then the test is once again inconclusive. So it will not work for everything. It needs to be some kind of limit that we can actually compute. And again, not 1. Okay, so that is the root test, and we're going to be looking at using it to determine convergence for some series in the upcoming videos.